Okay, so then our next speaker is Vova Sosnilo, and we talk about homotopy theory of stable categories.
Thanks. Thanks to the organizers for giving me the opportunity to speak here. Yeah, so today I want to speak about something that is based on a joint work of myself, Maxim Ramsey, Stefan Schwede, and Christoph Inges. But it's somewhat a technical topic, and I'm not sure how broad of the audience you are. So instead of giving like a talk about a specific thing that we did, I decided to give more of an overview of the whole picture that we are trying to develop or have developed in some aspects. So yeah, and for this I need to start from 100 years ago or so, maybe 8 years ago, and talk about the classical homotopy theory. And here it's very convenient for me that Urs have talked in length about cohomology theories, extraordinary cohomology theories, and things like that, because this is precisely the sort of context that I'm going to put all the things that we do here. So for topological spaces, we often consider cohomological invariants such as classical cohomology, K-theory, cobordism. So all of these cohomology theories, extraordinary and non-extraordinary. Sometimes you can also consider these twisted versions, but then they kind of depend not just on the topological space, but also on some extra datum here. And then you would have to consider kind of topological spaces with a choice of a twisting, so with a choice of a principal bundle, something like that. And in any case, people realize that many of the properties of topological spaces, which is a very transcendental invariant, it depends a lot on continuum amount of information for each topological space. And people found that all the important information, or a lot of the important information, is contained inside these cohomological invariants. So in principle, you want to consider some kind of version of the category of topological spaces where all of these cohomological invariants lived in a unique way, but at the same time, you don't remember all this unnecessary information that was sent to an equivalence by cohomological invariants. So formally, the way you can do it is you can look at all of your cohomological invariants, and you look at all maps between topological spaces such that all of your cohomological invariants induce an equivalence on this map. And then you form what's called the Dwyer-Kahn localization. So there is a categorical construction that for any category in principle, you can, oops, I need to rotate my tablet 1 second. Yeah, so for any category and for any class of morphisms, you can always consider this so-called Dwyer-Kahn localization, which is a universal functor that inverts a given set of morphisms. By inversion here, I mean that they're sent to equivalences or isomorphisms. And so in this situation, you can also, or at least if you restrict your attention to nice topological spaces, you can also impose a nicer set of equivalences, and you don't have to talk about arbitrary maps that induce isomorphism on some abstract amount of cohomology theories. Instead, you can invert the projection map from the product of any topological space with the interval to the topological space you started with. Right, so yeah, this is the situation that is very well understood. And this localization that people consider is often what's called the infinity category of spaces, or sometimes people say infinity category of anima, infinity category of homotopy types. But now the idea is very similar in flavor to what Urs was talking about, that we want to extend this picture to more general situations where you don't just consider topological spaces, but more geometric type of objects. So objects like differential manifolds, orbifolds, algebraic varieties. So I come primarily from algebraic geometry, so a lot of the examples of this sort that I have in mind are algebraic varieties, but you can, on the next page, you can replace that with anything that you're interested in. So, and if you try this picture, so if you start from the category of algebraic varieties, and then you define what you mean by cohomological invariant, which is possible, you can also try to construct this category. And in this situation, certain problems arise. So in the topological situation, well, we can always form a localization. The Dwyer-Karl localization construction does not depend on anything. But the difference here is that if you simply take the category of algebraic varieties and you invert something that you may call algebraic homotopy equivalences, so something that induces equivalence in all cohomology theories, then you will get some category that is not very well behaved. And one principal example of how badly that behaves is that this doesn't have essentially any colimits for any reasonable maps. For instance, it essentially doesn't have any cofibers along closed immersions. And to fix well, okay, so let me go back a little bit and say that in space, in the case of topological spaces, this is very well behaved. And first of all, this infinity category of spaces, it has all limits and colimits. And the colimits and limits that you get in some simple examples by taking, say, cofiber of a map or taking simple pullback diagrams, you recover some objects in topology that people were interested before homotopy theory was invented. So, for instance, if you have a continuous map from between two topological spaces from X to Y, then there is this construction called the cone construction, where you in classical topology, the way you define it is you glue together the product of the domain space with the interval and glue the point to one end of the interval and the target space to the other end of the interval. So yeah, geometrically it looks something like this. So you have some picture where this is fibered over X, and on one, sorry, this is fibered over the interval. And on one end, you just have one point, and on the other end, you have Y. So this is, yeah, this is the classical, this is one classical construction, which in the case of the infinity category of spaces is simply the cofiber of a map. And the other interesting example is the loop space, which is typically defined as the space of continuous maps from the circle to your given space, maybe with a base point fixed. And in homotopy theory, so in this infinity category of spaces, this can be recovered as taking the following pullback. So we take our space X, it has a base point, and we simply take the pullback of this diagram. This is going to recover as the loop space without ever talking about topologies on this base of functions or anything like that. So you don't need to think about compact open topologies, for instance. And more generally, this category is not only it has all limits and colimits, it also in the infinity categorical sense is a topos. Or at least, well, it is a topos, but what we care more about is that it's a presentable category. So essentially, it's defined by a finite, by a small amount of data, not finite. Right. So, and in the geometric situation, this doesn't quite work because the category of algebraic varieties itself is very small. You can try to enlarge it and consider the category of all schemes instead of algebraic varieties, but this is also not going to be enough. And one suggestion by Voevodsky was that instead of, I guess by Morel and Voevodsky, was to, instead of consider the category of varieties, you consider the category of presheaves on varieties. So you look at all contravariant functions from the category of varieties to the category of all sets. Or in fact, sets also turns out to be not enough, and you need to look at presheaves valued in simplicial sets or in topological spaces. So in any case, it's going to be an enormous category which does not correspond intuitively to how we think about geometric objects. It's extending too much. There are other approaches to this picture, and so instead of looking at the universal thing where you invert something, people also look at some stable versions of the theory, and in that situation, there is a nice approach by there is a nice approach using transfers. It's also by Voevodsky and by Suslin, whereas you instead of looking at the category of varieties, you look at the category of certain correspondences. So so the objects are the same, the objects are varieties, but the morphemes are going to be tuples of this kind, a map, another variety, a map on, and the two maps from the source and the target. And then under some assumptions, this turns out to recover the situation a bit better and recover more specific cohomology theories that one might care about. But in any case, the picture doesn't quite look similar to the topological one because you always have to enlarge, and you always have to do more than just localization. And this is the point where I'm entering the actual work that we did. And this is related to the so-called field of noncommutative geometry, where the main idea is that if you have, at least observably, in any geometric situation, usually you can look at your geometric object, and to that geometric object you can assign certain category of sheaves on that geometric objects. And these sheaves might respect the structure, the geometry that the space has. So for instance, you can look at coherent sheaves in the case of algebraic geometry. In certain differential geometric situation, you can look at sheaves with connections and more subtle structures. In any case, in all observable cases, there is a function of this kind. So if you're not familiar with varieties, you can think of any other category of geometric objects that you like, where to your variety you assign a certain category of sheaves on that. In algebraic geometry, we call this the category of perfect complexes. This category is that then satisfies a bunch of nice properties, and usually when you consider sheaves valued in vector spaces or in some other abelian kind of object, the sheaves are going to form what's called a stable infinity category. And I don't have time, I think, to give a definition of a proper definition of a stable infinity category, but morally, this is some infinity categorical analog of an abelian category. So it's a type of object where you have finite limits, finite colimits, and they are compatible in a certain way. And then all the home sets in this category, so pi0 of the mapping spaces, are going to be abelian groups. And in general, it's going to behave very similar to, say, the derived category of an abelian category. And so the idea is that if you look at this assignment, at least in algebraic geometry, so if you start from a variety, you assign it the category of perfect complexes, this remembers a lot about the original variety. So for instance, there's this nice theorem of Bondel and Orlov saying that if you have a smooth and proper algebraic variety over a field whose canonical sheaf or co-canonical sheaf is ample, one of the two, then the variety can be recovered from the category of perfect complex in a functorial way. Well, not in the functorial way, sorry, in a unique way. So you use the category, you use its automorphisms, and from this data you can recover the original variety. In general, this is not true. There are varieties that have the same category of perfect complexes. In this case, these varieties are called Moriti equivalent sometimes. And this also turns out to have some drastic implications to how the cohomology of these varieties behave. There are a bunch of conjectures saying that in this case, all Hodge numbers should coincide. All of these kind of forces you to think that maybe instead of studying the geometric objects themselves, you could study all stable categories as geometric objects. And this last sentence that I said is precisely the origin of noncommutative geometry. This is how all these people develop in that thought that we could just instead of looking at some nice geometric object, we can look at abstract, very categorical, very algebraic object. And nevertheless, a lot of the theory that you have for geometric objects is generalized to this case. In one reason to think that this might be a good idea is the fact that some of the more important cohomology theories that we care about, namely K-theory and also Hochschild homology, are defined for these categories. So, okay, Hochschild homology might not sound too important for many of you, but it's the algebraic analog of the ramp differentials. So essentially all the algebra that you can do with the ramp differentials, you can do with stable categories and not a geometric object. And similarly, you can also define K-theory, which is something that usually studies bundles on a variety. And here it just defined functorially globally on all stable categories. Right. And so in this situation, we can try to mimic the picture that I already drew twice before. First of all, there is a very nice definition of a cohomology theory of stable categories, which is called a localizing invariant. I don't really have time to define it, but this is a very natural definition which uses very little information about stable categories. It essentially works in any category of finite limits, infinite colimits. In any such case, you can define what localized invariant would mean. So it's essentially a categorical notion. But in this situation, it actually recovers all the, it is satisfied for, so the property of being localizing is satisfied for things like K-theory, or things like Hochschild homology, Zellmer K-theory. So for a bunch of practical examples, it's satisfied. And it also looks like everything that we can do with those invariants, we can do with arbitrary localizing invariants. And you can mimic the definition that I suggested in the very beginning, that you say that the map of stable categories is a motivic equivalence if any localizing invariant induces an equivalence on it. So, and then you can form this you can try to localize with respect to this set of maps, and you will get something, but in principle it sounds quite unreasonable that you get something good. But this is a theorem that we actually prove that you do get something good. You get a presentable category, which is also stable. So in some sense, if you look at the picture from the very beginning, you start from spaces, then you generalize to some geometric objects, which are more hard to which are not as soft as topological spaces. It's harder to make right definitions. You don't get you wouldn't get the right category. But when you pass to stable categories, the situation becomes soft again, and you can define you can define the right category of homotopy types just by inverting certain morphisms. And here, okay, so I guess I'm kind of almost out of time, but let me just mention that this has a corollary, which, well, it's not a simple corollary. You need to work a little bit on that, and you need to know how exactly this theorem was proven. But one corollary of that is the following. It was asked by Kovanov in the paper Categorification and Linearization. And he asked whether, given an associative ring, everything is classical, not a ring spectrum, just a ring, whether you can find a monoidal triangulated category whose K0 is going to be that ring. And so the theorem above allows you to show this, and moreover, it allows you to show the analog for arbitrary ring spectra. So in fact, we can build the K-theory spectrum of any monoidal stable infinity category. It's going to be an associative ring spectrum, and for any ring spectrum, you can also recover that. Well, okay, I guess I'm kind of out of time. So
if you want, you still have like 5 minutes or so because we started later. So up to you.
Okay. Okay. Yeah, this is good. So in this case, I want to say a few more words about how this theorem is proved. I don't have handwritten slides for this, but I hope that's okay. So classically, the way it works is that those localizations, both in the case of algebraic geometry, where you take the pre-sheaves and varieties and you invert motivic equivalences, or in topology, where you invert homotopy equivalences between topological spaces, these are examples of what's called Quillen model categories. So you have a category, you have a certain class of morphisms which you want to invert, but then you also have two additional classes called cofibrations and fibrations, and all of them together interact in such a way that you can deduce a lot about the localization. In particular, this is how you typically prove presentability, or prove that there is enough co-limits and limits. You show that in any model category, this is true. If you have a model category, you localize it, you end up having a presentable, well, any combinatorial model category, I guess, combinatorial cofibrantly generated model category, you'll get a presentable category as a localization, presentable infinity category. And in this case, we observe that it's kind of similar, but you don't quite have the theory of Quillen model categories. And instead, you have the theory of cofibration categories that comes into play. So the idea is model category consists of, well, you have a category, you have class of weak equivalences, then you have class of cofibrations and fibrations. And the way it's set up, it's kind of self-dual. Like if you replace those, if you if you take the dual category, the two classes just dualize, and you still get a model category. But in principle, it doesn't make sense to consider this like localizations and categories in general, like presentable categories in general, is not a self-dual notion. And if you want to recover something that is presentable, if you want to recover something that has, say, colimits, you don't need this duality. You only need one part of it. And this comes from the theory of cofibration categories, where you guessed it, you only have a category, you have a class of weak equivalences and cofibrations, but you don't have any fibrations. And then there are some compatibilities very similar to the ones in the model category, which turn out to be enough to show statements like this, to show the existence of colimits, presentability. And in our case, in the case of category of stable categories, so when C is cat stable, we define, well, weak equivalences the way I told you before. We define them to be motivic equivalences, and cofibrations are given by fully faithful functors. And so with this setup, surprisingly, it's pretty easy to prove everything you need. So you just need to show that you need to verify those axioms, and then in the end you need to show that in the category of stable categories there exists kind of a delooping functor automatically, given by something called Grayson construction, which automatically shows that the localization is going to be stable. Okay, now I think that's all I have to say for you.
Okay, let's thank the speaker. And we do have some time for questions if people want to unmute themselves or raise their hand.
Can you maybe, thanks for the talk first. Can you say a little bit more about that caveat with Voivodsky that you talked about? Why do you have to enlarge the category of algebraic varieties? What for?
Right. So, well, the stupid reason, if you look, is it here or is it before? I think it's before. Sorry, I'm lost in my slides. Right. So the problem here is, first of all, the category of algebraic varieties, if by a variety you mean something like finite type separated scheme over a field or something like this, it doesn't have all limits and all colimits. So already this poses some issue. You cannot really you cannot really use all this machinery of model categories. So it's reasonable to enlarge. But there are some other more geometric enlargements. So there is a category of schemes, and that also suffers from the problem that it doesn't have arbitrary limits. This is already a subtle fact, but in the category of schemes, only limits along affine morphisms. So at least filtered limits only along affine transition morphisms exist. In general, limits just don't exist. And again, you cannot hope for a nice way of controlling the localization.
All right, so you can define the localization, but you can control it by
yeah.
Okay, I see.
I was a little bit vague about this. So I mean, okay, of course we do want some category that is like universal in the way that all cohomological invariance factor through this, but we also want something that behaves in a way. I didn't really talk about this, but we really want that this category kind of looks like a target of a cohomology theory. The thing is, it's a much more subtle task, and it consists of some categorical properties of this localization, which ultimately we want to control. So it's we can always form a localization, that's true, but then it's not going to be exactly the right category. It's not going to be something that one would call motivic category, the category of motives.
Okay, thanks.
Thanks for the question.